Over to you. Thank you.
Okay, let me share my screen. Can you see my screen, Greg?
Yes, very good.
Yeah. Okay, that sounds good. Okay, thank you very much, Greg, and hello everyone. Good morning and greetings from hot and humid Tokyo here. I'm sure that you all are enjoying your winter over there, and I'll be back joining you all in about a week. So today, I am speaking as the theme leader of the third theme that is titled Fit for Purpose Components. It focuses mainly on non-structural components of buildings. So as Greg mentioned, I and Rashid will give you some overview of what we have been doing so far in this theme, as a part of this theme, and what our plan is for the next couple of years. And of course, to get the valuable feedback from you if there is anything that we could do slightly differently. So let's start. So this will be like, like trying to preach the converted, but just to give you a brief overview of what non-structural elements are, or what is the scope of the theme, is actually anything in the building, any part of the building that does not participate in the gravity and lateral load transfer. For example, the structural system, which are beams, columns, slabs, foundations. So they are the structural members, and anything other than that, right, that does not participate in this load transfer, we call them non-structural elements. So in broad classification, we classified them into two categories, acceleration sensitive and drift sensitive. And those components which are connected to slabs or hanging from slabs, braced to floors, they respond to the acceleration, and they are damaged because of the large inertial forces. So they are acceleration sensitive, whereas the vertical elements like the partition walls or windows, glazing, cladding, they are connected to two different floors of the building, and they respond to the drift or deformation of the building. They are called drift sensitive. So we have done some research in terms of like how much they contribute to the overall building portfolio. And what happened? Yeah. So if you look at the building value, the asset value of a building, and break it down into how much of a building value comes from construction cost, and within that, how much comes from structural components and non-structural, drift sensitive and acceleration sensitive. This is how the breakdown looks like for different types of different uses of buildings. So for most buildings, the exception is the third type, which is like outdoor sports facilities or parking garages, where you don't have any partition walls or ceilings. It is only the bare structural skeleton, right? That's where, understandably, the structure dominates the overall value. But for all other types of buildings that we use, you can see that the structure only contributes to 20% or less. And majority of the value comes from non-structural elements and equipments, right? So not only that in the building value, but even after an earthquake, obviously building can suffer damage, and in order to restore the building, we need to repair a lot of damage, and not accounting for the business interruption, just the direct repair cost. If you break down the direct repair cost into how much of that is coming from repair or damage to non-structural elements and structural elements, you can see this is a typical case for standard reinforced concrete frame office building in Christchurch, and it only about 25% comes from structural repair. All others are due to non-structural repair. So obviously, these are evidences, if one needs any, that non-structural elements are more important than structures in terms of these, value proposition as well as loss minimization. And we have to give much importance to them. And you might have already seen some of these photos, and you might have observed yourself the damage to non-structural components in recent earthquakes in New Zealand and even in overseas. So one example is actually the middle figure there on the right. You can see sprinkler head tearing through a ceiling panel, and quite a large length of the ceiling panel was torn off. And basically, based on our mechanics theory, we can never get an estimation of that level of damage, that extent of tearing through, because interstory drift from in a building at a small earthquake like the Seddon earthquake 2013. And this is a photo from BNZ building in Wellington. And because we had damages like this, and the non-structural damage mainly, the building had to be closed or out of operation for, I don't know the exact amount, but almost about 2 months, I heard. There was absolutely nothing, no damage to structural system, because the shaking was not great, not large. It was not above moderate by any means. So there are many stories like this. So we have got a lot of instances or examples of non-structural damage when the structure is performing well. So as I indicated earlier, non-structural damages and non-structural elements are crucial for continued functionality of the buildings as well, not just for repair cost, because it includes many operationally critical components like air conditioning, heating and ventilation system, lighting system, plumbing. So these, if these are damaged and you don't have the services provided in your building, they can be out of service, out of function for quite a while. New Zealand experience in Canterbury earthquake sequence, you might recall that in September 2010, we had, in general, like moderate to severe damage to our non-structural components, when the damage to our structural components was only minor. And in February 2011, the Christchurch earthquake, we had the structural system suffering moderate to severe damage, but the non-structural elements, there were many instances of severe damage and collapse of non-structural elements. So you can always, one felt that actually there is just one step more damage, one step of higher extent of damage to non-structural components compared to the structural system. So clearly there is a mismatch between the performances of structure and non-structural components. And that is understandable, because we haven't been focusing a lot on improving the resilience of our non-structural elements in the past. And obviously the awareness has increased now, but in the past we were mainly focusing on structural resilience, and which did reflect in improved performance of structure compared to non-structural elements. And they obviously non-structural and contents damage contributed significantly to the financial loss and downtime. And not only loss and downtime, if you look at some of these photos of damage to non-structural elements, we were lucky that actually we didn't have any casualty because of non-structural damage, but it was a matter of luck and timing, and these type of damage can easily kill people. So also for life safety, they are important and they can be important. We have evidence of people being killed due to non-structural damage in 2016 Tohoku earthquake in Japan. People were killed because of the ceiling and the services from above falling down in a swimming pool. Ensuring consistency between non-structural elements and structural system is like, the structural system obviously decides or dictates how much demand comes on non-structural elements, like depending on whether you have a frame system or a wall system or a braced frame, you can have different acceleration demand and drift demand for your non-structural components. But we can design the non-structural elements to accommodate the demand as long as we know the demand, and we have been developing technologies that can accommodate larger demand non-structural technologies, and we obviously there is more work to be done, so we are still working on those, developing smarter and resilient solutions for non-structural components. One thing I want to highlight is, like the drift or acceleration capacity of non-structural elements. In order to enhance their resistance, we don't need to spend a lot of new and more materials. So it is just doing or thinking about their connection with the structural system, their classes with other non-structural components, and providing the clearance, required clearance, and coming up with maybe flexible connections and the way that they behave uncoupled with the structural system. So it is not necessary that a more resilient non-structural component is more costly. Okay, so any increase in cost of low damage non-structural elements will be modest. So after like going through all these recent experiences of damage to non-structural elements and disproportionately large contribution to the overall loss in earthquakes, the international non-structural community gathered together and they started a new organization to facilitate collaboration between industry people, practitioners, researchers, and just gather the data related to non-structural elements and foster, overall development of new technologies and adaptation of that in industry. So the association called SPONS, the acronym stands for Seismic Performance of Non-Structural Elements. So that was established in 2014, and there are representatives from New Zealand in SPONS, and we have got a couple of directors in its board. I'm currently the president of this association for this term, which I was elected last year. And even in New Zealand, like after the earthquakes, the awareness and even the resources coming to non-structural elements did increase. And we did quite a bit of research even before the Building Innovation Partnership to understand the critical weakness of how we do construct, design, and fabricate these non-structural elements. So there was quite a bit of work done in terms of cladding, partition walls, and ceilings, and interaction between different components. But the work or the information that we gathered through that through those projects actually were not enough for us to come up with or to solve the problem as such. So part of BIP, the theme 3, we decided to focus on non-structural elements and take the learnings from our previous projects further and come up with some solutions to address some of the key problems. So at the moment, actually, the focus is on two aspects. One is understanding procedural and technical weaknesses. I highlight the procedural there because the weaknesses that exist are not just technical weaknesses. Even in terms of procedure, procurement, and installation practices, there are weaknesses. So the idea or the aim is to understand that those weaknesses so that we can address them in the next phase. So we did complete a project where we consulted industry and then came up with a white paper highlighting, like the current state of practice, what are the issues, how we can improve it. And there are experimental projects to understand the technical weaknesses, which are ongoing as well. And the second part of this BIP Theme 3 project, second objective is to enhance the seismic performance of non-structural elements. And these projects do cover both drift and acceleration sensitive components, non-structural elements. We investigate, like design and assessment needs related to non-structural elements. As you might have been aware that actually we have been using the structural seismic performance assessment methodology. And if we want to not just concentrate on life safety, but want to also assess the resilience of a building, we cannot leave the non-structural elements aside. So we have to develop guidelines and methodology to assess the performance, likely seismic performance of non-structural elements. And we also want to develop novel and smart technologies for different non-structural components. And we want to validate the system level, not just the component level performance, but the system level performance, which accounts for interaction between multiple components and also the interaction with the structural systems. And a small part of these projects also look into multi-hazard, or especially dual hazard, going beyond the earthquake only and combining earthquake hazard with fire in one project and water tightness, weather tightness in another project. So potential benefits and impacts of these projects range between across the amendment of non-structural elements related seismic design provisions, because the knowledge that we gather from these projects will feed into the revision of non-structural elements design provisions. And also, as I mentioned earlier, seismic assessment guidelines for non-structural elements. And there will be low damage technologies that will be developed through these projects, and smarter connections between non-structural elements and structure. And New Zealand's, standing as one of the leading research organization or research institution internationally, and that is evident through our prominent presence in an international organization like SPONS. So just to give you a brief overview of some of the projects that we are doing and we are planning to do, is actually one of the projects is looking at seismic performance of sprinkler systems, and Rashid, who will present after me, actually he finished his PhD working on this project very recently, and we did test a large number of configuration of the sprinkler systems in terms of plenum depth, different pipe sizes, different bracing configuration, and we tested them against different types of floor motions, like floor motions that are that have similar frequency characteristics with the piping system. Means like there is resonance and there are non-resonant motions as well. So we just wanted to understand better actually the system level performance of these sprinkler systems and how we can improve their seismic design. So the outcomes are published and are being published in international journals and in NZSE bulletin as well, which are available to you. The other project that is affiliated with BIP Theme 3 and co-funded by Natural Hazards Research Platform as well was looking at the performance of glazing system, and not just the seismic performance or the structural mechanical performance, but also weather tightness, water tightness. Right. So for this, we did develop a unique testing frame and testing rig and testing methodology, I should say, where you load a large scale glazing panel in a cyclic reverse cyclic loading, and in between you also apply sprinkler water under a pressure difference between one side and the other side, mimicking what happens in reality in buildings, building windows, and then when we start seeing leakage of water and on the window. So after an earthquake, actually, we might only try to look at physical damage to the rubber gasket or glasses, and we don't see any damage, and we rest assured that, okay, my system has performed well. But one of the key objectives of glazing system is also to protect you from water leakage and air flow, or provide the insulation as well. So what we notice is actually, although the structural system or the glazing system that we use currently requires a large drift before any physical damage happens, but water leakage can start very early, right? So as early as maybe only when it is 0.2, 0.3% drift, which can happen in even minor shaking, right? Whereas by using smarter and seismic frame and structurally glazed silicon frame, we can definitely improve the water tightness as well. There is smaller difference between these different systems when it comes to the physical damage, the fragility for physical damage. But if you look at the difference in their performances, standard glazing versus seismic glazing, you could see a significant difference in terms of their water tightness or the water leakage. And the other project that we just finished, Jitendra, another PhD student who graduated last month, we finished his PhD last month, looked at developing low damage rocking cladding panels, and this has been widely published now in journals. So the idea was to, rather than make the cladding panels deform together with the structural system, we allow the cladding panel to remain in its position while the structure deforms by enabling them to rock, respond in a rocking motion. So the idea is, if we allow rocking, we can control the amount of rocking displacement because just that simple equation, the drift that we want to accommodate can be simply related to the rocking allowance y, and r is the radius about which it rocks, right? Or the dimension of rocking arm length. Right? And similarly, between different panels, we have to use sealants to join them, and they are vulnerable to damage, but we can control their damage as well by just simply applying the basic mechanics. And if we know the sealant property about on how much shear deformation it can take before it starts tearing off, we can control that by design. So by applying this concept, we came up with the idea of like precast concrete rocking panel, which has 4 steel embeds that allows or enables rocking motion, and 2 weld plates that are used to transfer the gravity load of these panels and also provide provide a rocking interface, so that there is no stress concentration on the concrete and there is no localized crossing of concrete. So we have done a large number of tests on these type of panels, cladding panels, and you can see right top there the video, the animation there, where you can see even up to like 3%, 4% intrastory drift. It does guarantee that the glazing, the cladding panel does not incur any damage whatsoever. And at a larger drift of beyond 2.5%, you will see some minor tearing, partial tearing of those sealant joint in between different panels. And not only this test, but we also did a test in our lab to look at what happens when we have multiple story of these panels, and there are vertical connection as well as horizontal connection. So it is like kind of like 2x2 panel grid that we applied, and when we tested, we could validate the performance of these sub-assemblies as well. There was no damage whatsoever to the panels and the connections, so only damage was to the sealant joints, and the signs of damage started after about 1.5% damage, 1.5% drift. So up to then, actually, you can completely remain, or this system does not need any repair whatsoever. And the other project that Jitendra also did was to come up with a low damage rocking partition wall, and similar concept to the cladding panel. We tried to apply the enable rocking motion of the partition walls, but without having a wide vertical joints. Okay, so in the previous version that we worked in before the BIP program, we had a large gap vertically between the structural frame and the non-structural wall, and also in between different wall panels. So that required quite expensive and extensive, like sealant application to fill those gaps to get limited drift capacity. But here in this project, our idea was to avoid those wide gaps in the vertical element and provide at the top, which is hidden naturally by the track, the top track. So you don't need to fill those by the sealant because the track will cover that anyway, right? So in order to apply rocking motion, and there were some complications, especially when we applied this to steel frame partition walls, drywall partitions, because the steel studs can locally damage when we force them to rock about these steel studs. So we had to improvise a few things like packing the steel stud with a small timber plank near the end, so that there is some stability of that steel stud when it rocks, and applying an aluminum angle to pull the whole wall while it is rocking. So all those things were applied, and finally we came up with a solution that does work quite well. So this video animation shows the performance of this type of wall until beyond 2% drift. We don't get any damage that requires repair up to 2%, and only around 2% you see some minor screw impressions. Right, so you can design the clearance at the top as per your need, your design drift demand, right? So if your design drift is 2.5%, as we use in our flex,
Yes, so I'll introduce the seismic qualification framework for non-structural elements in New Zealand. So BIP did a white paper on the design and construction issues related to non-structural elements. It was led by both industry and academics. And one of the major recommendations from that white paper was that we need a test facility for non-structural elements in New Zealand. We tested that hypothesis in a grants-funded project. We interviewed different professionals from across the industry. We interviewed structural engineers, non-structural engineers, fire engineers, suppliers of equipment in New Zealand, building control officials. And what we found in that project instead was that we need a qualification framework for non-structural elements before we can establish a test facility. So the idea of the qualification framework is to establish minimum standards with regard to the seismic design of these elements. Why do we need a qualification framework? Because the building code provisions are very vague with regard to the whole of building performance requirements. So that means that we are not very clear on how the entire facility performs according to the building standards. So when we have a, let's say, a hospital building, and you want it to be functional after an earthquake, we should have designed the structural part and the non-structural part in order to maintain its functional after an earthquake. But currently, the design standards are not very clear on how we design different non-structural elements in order to achieve such performance targets. So the framework would harmonize structural and non-structural performance with the target to achieve what we have for different importance levels in the building code. And we will be looking at functional performance, which is going beyond the seismic restraint. So seismic restraint itself is good for resisting the seismic actions, but it does not provide as much information on whether or not a certain service or utility inside the building will continue functional after an earthquake. Another major question in the industry is that how do we validate performance of, for example, generators or boilers inside buildings? So this question whether or not we need to test or not test, because the standards are quite on this. So we need a discussion on this. And finally, another problem is the product substitution. So if a product is specified for installation in buildings, sometimes it's substituted by something that has a lesser cost, but that product may not deliver the required performance and can really hurt performance of buildings in earthquakes. The qualification framework will have three aspects. So characterization, specification, and quality assurance. So starting with characterization, it will first clarify performance requirements. So let's say we have a glazing panel on the outside of the building, which could lose its weather tightness during earthquake. So what will be the consequences of losing weather tightness of a glazing panel for the facility as a whole to continue functioning or to be immediately occupiable after an earthquake? So we quantify such capacities, such performances using different design procedures and test protocols. But before we can do so, we need to agree on some simple design procedures that could be used in the design offices. And we also need to agree on some test protocols. So if we need to test a generator for functioning of the hospital, what protocols do we use for its dynamic testing in labs? And once we have this data from characterization, it feeds into a specification document. So what a specification document does is that it outlines different components available for the same function in New Zealand industry. And then based on what a building requires, we just simply choose the required component from the specification document. Let's say we have a hospital building and we calculate how much is it going to shake during an earthquake. But we require a specific equipment for that hospital to continue functioning after an earthquake. We just go to the specification document, pick the required component at the required shaking level. And then finally, quality assurance would provide procedures for reviews and inspections so that we make sure that we install the right components in the right building. Implementation pathway for the framework would be, it's a long-term project. Currently, we are here. We have already developed a team which consists of a structural engineer, non-structural engineer, contractor, project manager, quality assurance experts, academics, and developer. In the next 6 to 9 months, we are planning to complete phase 1. We will be submitting our funding proposal to grants. And under phase 1, we will conduct a gap analysis, which would provide us knowledge and design tool gaps that we would fill through industry experience on real projects, supplier data on equipment or say partition walls design, And we have some state-of-the-art research work in New Zealand. So we will bring these three sources of data together to fill the gaps in the three aspects of the qualification framework. And once we have the structure of the framework, we take this framework to a community of practice, which would be more or less the same as our team, but others are invited to join and test this framework on live projects. And the feedback that we get from this testing and trialing on real project would actually be used to make the framework more and more practical and robust. In the next 2 to 5 years, we develop guidelines for broader industry. That would be through workshops and guidelines documents. And we can also collaborate with industry organizations such as AWCI to promote the implementation of the framework. And the 10 to 15 years plan is to make the framework a part of regulation by employing verification methods and acceptable solutions. The lead team has it's a very robust team. So we have academic structural engineers, non-structural engineers, quality assurance experts, and a representative from brands, project managers, contractors, and we plan to bring on a developer. And we have already, like I said, finalized the team. We will be submitting the proposal in a few weeks. And this framework also links strongly with another project that has currently been submitted to EQC, and we're waiting their approval. So the purpose of that project is to develop strategies for seismic retrofit of buildings. And the focus is on whole of life and whole of building performance. So how a building perform over its life, not just to earthquakes, but also other factors such as carbon emissions and functional performance. But in order to achieve such objectives, we really need to bring together structural and non-structural performance and design both in a manner that we achieve different performance targets at different stages in the life of a building. And we will also utilize some BIM technologies which are gaining momentum in New Zealand, such as BIM. So finally, what is the way forward in Team 3? We have a very broad and practical vision. So the development of the qualification framework is a big project, but this is something that is very essential for the industry. It will be undergirded by practical industry experience and state-of-the-art research, and it will result in high-quality buildings, by which I mean it will reduce risk and increase our confidence in achieving societal expectations for our buildings. And it will also cause positive impact through the supply chain because there will be more transparency with regard to the selection and installation of components. Shouldn't have any questions.
Yeah, thanks. Good time. I don't think Doc just has arrived back. Perhaps we could take some questions for
Yeah.
Any questions?
Sorry, Greg. Sorry, everyone. I don't realize actually. I didn't realize where I broke actually. Where was I?
Good question.
Oh my gosh, sorry, I'm extremely sorry. Yeah, the system just turned off here. Yeah.
So hold on. So we filled in. So Rashid has covered the seismic qualification framework. So we'll just take some questions for Rashid.
Okay,
we'll
that's
come
fine.
back, and I think I can tell you where
Yeah.
Any questions? Yes.
Yeah, so it sounds like a very solid process for new builds. Is there anything similar in the pipeline for existing buildings where we assess the safety of existing systems? Because that's what's going to cause the most harm in the next place, right? The existing buildings, not the new builds that are especially after this process.
Yeah, I think we can assess the adequacy of different non-structural elements by using the guidelines from the characterization part.
Yeah.
So if you're talking about just designs, I think we have some, we are planning to develop some assessment procedures that could be applied both to new buildings and existing buildings as well. And secondly, the specification framework would also help in assessing existing buildings. So I do not have it here on the slide, but the specification framework essentially includes a table. We are proposing 5 non-structural classes. Each class would be associated with a certain acceleration or drift capacity for a non-structural element. And these capacities will be associated with, say, serviceability limit states and ultimate. So once we have that information for an existing building, the expected drift or accelerations in an earthquake of certain intensity, we can easily assess whether the installed non-structural elements is adequate or not by employing the design procedures in characterization. And we are planning to keep these simple and practical, like you can utilize them by using an Excel sheet with just some hand-based calculations.
And then, is there any plans to cooperate with councils, local councils, or so? Because building owners wouldn't necessarily go back to reassess their buildings until someone forces them to do that, right? Because there might be cost, or that building might not be fit for purpose anymore. Is there any intention to work with local councils on that?
Not now, but along the implementation pathway, yes, surely we would need to do that. Like I said here, we would have to deliver it to the broader industry. So, yeah.
Another aspect for that is we see a lot of upgrades in the next years. So that's definitely due to decarbonisation. Like taking coal boilers out and putting electric boilers in, all of this, which leads to changes in platforms and like some sorts of things that are full of building services. So I think a really important component here is to look at the interface between existing building services and new building services and their strategy of restraining them, because if we restrain new parts but have all parts cashed into that because they're not restrained to the same accelerations or calculations or even standards, because we're going back 50 years, 60 years, etc. I think with as an industry, we need to agree on something to be competitive here, because if we provide cheap designs by not taking these things into considerations or cheap installations, we will end up with an even bigger risk for our hospitals, etc., especially those important buildings. So I think it's an extremely important topic that's hitting us right now with all of the changes due to the pandemic.
Yes, so we are planning to take an agile approach, develop this for different phases. And at the end of each phase, we intend to deliver a product that could be usable in the industry. So yeah, I will make a note of this and convey to our team that we do need to deliver something that could help with such cases or retrofit of buildings that is going to happen over the next 1 year or two. So we do plan to take an agile approach so that we can deliver something, whatever is possible, whatever we have knowledge on and experience on, deliver that to the industry so that people can use it for projects that are being planned to be upgraded in the next 1 year or two. Yeah, so the first phase would be 6 to 9 months, and I hope we have data on assessment procedures. We could deliver those.
Yeah, thanks for that, because retrofits is a big issue, and it certainly is on our plan to look at retrofits as part of the next 4 years. Thank you for raising that. It's good to hear. That's important.
Yeah, because the retrofit thing, but also so with that, I think it's been quite more around the star rating and stuff, you know, coordinate with that so that when people are looking at existing new buildings, they take into account both structure and construction.
Yes, we did interact with QuakeCore last week. Did present this idea there.
Rashid, can you repeat the question, because we cannot hear the question well? So maybe before you address, maybe just repeat the question and then address it.
So the recommendation is to interact with QuakeCore because they are working on the assessment of buildings, and they have a class system to assess different buildings. So I did a presentation to QuakeCore last week and did discuss this idea. So whatever they are working on structure with regard to structural performance, the findings or the recommendations from the framework could be used to couple the two and assess whole of building solutions and strategies.
Yeah, Rashid, I think in order to, I want to add on that, because we already are working with QuakeCore, because I am taking care of the QuakeCore, like whole of building performance. There is an objective on non-structural elements part, and I am leading that part. And the project that I mentioned about the multiple non-structural elements, the tests ongoing in the lab, Robert's master's project that is co-funded by QuakeCore, and they are fully aware of the things that we are doing, and we are trying to match with the whole of building performance objectives there. So there is, in addition to what Rashid mentioned, there is much more going on here.
Yes. Questions to the council, asset manager for M3 Waters. So one of the questions is, interesting stuff, vehicle for change, if water reform, literally, let's have its day. Part of the aspirational goals of water reform is the transformational side of things. So in terms of resilience, there's going to be an awful lot of assessing what we have right across the country in terms of the 3 waters networks, 2 waters. So all your pump stations, treatment plants, and everything else like that. So if you're looking for a vehicle on which to incorporate some of your findings, potentially some of the benefits, bigger picture, resilience, recovery, post-event, I think of AFA straight off the bat, do you think that would be a good tool that we could sort of add to the transformational part of water reform, say, if it goes ahead?
Yes, I think we have a similar vision for non-structural elements. Not just like I said here, it's not just seismic restraint and restraining things, but we are looking at functional performance. And this is not just limited to earthquakes as well. For example, if we install a partition wall inside a building, that partition wall, in addition to fulfilling the performance requirements for earthquake, should also fulfill the acoustics and fire as well. So the idea of the framework is that anything that we install in the building should fulfill the different requirements for different environmental conditions. So it's not just limited to just earthquakes or just one scenario. So it has a broader vision. Install things based on the like the whole of life and whole of building performance. It should contribute towards how that facility as a whole behaves and how it behaves at different stages along the life of the building. Obviously, there would be different conditions, fires, or rains, or weather tightness issues, and obviously earthquakes.
So, I mean, thank you for that, because part of the program doesn't include at this stage the resilience of horizontal infrastructure, but you can see there's a connection.
Oh, totally.
And so we'll definitely go back and have a look and see whether we can leverage off this project to support the resilience of horizontal infrastructure.
Well, I was just thinking while that was up. So I sit on for NCD as part of the transition unit for water reform. That aspirational goals, etc., comes after. But it would be worth literally just getting that on the agenda, and just literally making the rest of NZ know that UC are looking at the, through UC are looking at this. Because again, one of the things that we're looking at is open source data to academia. So we release more and more data, so people like yourselves can literally take those data sets and literally start interrogating.
Thanks. Are you looking at excuse me, components that can be used structurally or non-structurally, and whether they should be structural or
not? Not now, but we can consider it. It's a good suggestion. So the first stage, phase 1, would involve gap analysis, which would answer questions like these. So we will.
Rashid, what is the comment or question, please?
Yeah. So how do we deal with components that can serve a structural and non-structural performance?
Oh, okay. Yeah. Please proceed. Yeah.
Yes. So gap analysis would include what are the most common non-structural elements that are used in building, and at least provide guidance on those elements. Obviously, there will be some components that are specific to a certain type of building, such as hospital or say data centers. But we do plan to look into all these details. We cannot have your comment.
on timber frame buildings with diagonal bracing and normal jib, in which case it's non-structural, versus the same timber frame building, no diagonal bracing and bracing jib.
Okay, yeah, I will note that and look into this and present it to this idea.
Yeah, that obviously has implications for the residential as well as the commercial space. This is not simply a commercial product. We think it covers the gamut.
I live up near the epicentre, and half my neighbours were three building code change, half the post, and every bracing gym house we built, the older homes with bracing.
Yes, thank you.
How do you see this qualification fitting in with the building code and other legislation?
Yeah, so we initially planned to release this as a, sorry.
If you could just repeat the question, because the folks at home are finding it hard to get.
Yeah, so the question is that how would the framework be in the building code and design standards? So initially we planned to release the various deliverables as guidance documents. And we would need to look at what the building code requires for building buildings of different importance levels. So it will be guidance that we would provide in the framework would be in line with what building code requires, and also provide more clarification on the wordings in the standard. For example, the word operational in, say, for example, the standard for sprinkler systems is very unclear, that what exactly would make a sprinkler system dysfunctional during an earthquake. If we don't know such criteria, we don't know what to design for in order to maintain its functionality. So we would look into such questions, and once these guidance documents are developed and the industry adopts them, then we can make a push for making a part of the regulation. But it's not, the framework itself is not something that will be developed from scratch. We have a lot of data already. We want to bring that together and provide guidance so that we can fulfill the requirements in the building code and the design standards. Obviously, we would have some gaps that would need to be filled through research, and some feedback would be provided by testing it on live projects as well. So over the passage of time, we would see what gaps do we have that prevents linking it with the building code and design standards.
Okay, thank you. I think it's time to move on. I think we might just pop back to Rajesh, if that's okay. Thank you very much for sharing. Very well done.
Shall I stop sharing, Rajesh?
No, that's fine. I think because I understand that I was towards the end of my presentation, was I? Or yeah, so
you need to start here with Robert's project.
Okay, I see. So I think there is only two because yeah. So can you just go to next slide, please? Yeah, so this Robert's project was actually what I indicated about the collaboration with Quake Core, right? It is testing multiple non-structural elements, but this project here on the slide is about, like where we look at multiple hazards. So in addition to these earthquakes, we mix that with the fire performance as well. So looking at the fire stopping efficiency of fire stoppers after seismic movements. So in this project, we intend to do small scale test in a university lab, and then follow that by the large scale test at branch. So the idea is to understand the residual performance after the earthquakes and develop a kind of like validation methodology for fire stopping system, because we are working together with Hilti on this project, Hilti and branch. So they are providing us a lot of information about the existing state of practice, and we are not just looking at the component performance of Hilti products, but overall a bigger picture in terms of how we can establish a methodology to help the industry to look at these aspects and design for better performance. And the final, next slide, yeah. And the final project that we are planning and ongoing is actually about a 3-story building, full-scale building test. Like you can see the size there, 5 meter by 8 meter on plan, and then 10 meter height means 3-story full scale. It has multiple non-structural elements. Can you click again? Yeah, so it has multiple non-structural elements attached to the building. You can see the suspended ceilings in level 2 and 3, partition walls of different configuration in level 1, precast cladding panel and glazing walls in 2 opposite corners of the buildings. Like 2 diagonally opposite corners will have cladding, and the other 2 will have glass curtain walls. And then we'll have sprinkler pipes in level 2 and 3, and some contents in level 3. So it will be tested on a big, large shaking table facility in China, utilizing 2 tables together to support this building. We will apply a series of earthquakes in 1 direction as well as 2 directions to test not just the component performance, but their system level performance. Actually, how do they behave when they are part of a building, not just they are tested on their own in a cyclic testing setup that we did at Canterbury. So this project is obviously quite ambitious. There are many parties which are collaborating with us in this project. There is a huge team from China and University of Auckland and Auckland University of Technology. Unfortunately, the students that were working on this project are now graduated because of the COVID-19. The project has been delayed quite substantially. We were planning to test this in 2020. Looks like we have to wait until the beginning of next year to do the test. Most of the preparation is already done, but we are not able to travel to China at this moment. And we are in the process of hiring a new PhD student to work on this from now on, taking over from Rashid and another student, Jitendra. Can you go to the other slide? Yeah, so as I mentioned, the research that we do in this project, BIP Theme 3, are mainly to understand the critical weakness and to develop low damage technologies for non-structural elements. But there are also efforts which are aiming to develop guidance and methodology framework to improve the efficiency and consistency of a non-structural design. And Rashid already presented about one such effect, right? Please click once. Yeah, you can see the example of design inconsistency here. Like this is an example of, like how different guidelines at the moment, different design standards provide you the design demand for the same acceleration sensitive components on the same floor of the same building on the same location. Right. So if you apply different standards, you will get different design force, and they are quite substantially different. So not all of them can be right. And this is mainly because of, no unanimity in the current state of knowledge. So it has to improve. Click again, please. So despite all the ongoing efforts from research, actually, there are still quite substantial issues, like we are facing due to these highlighted points, like inadequate procurement practice, tendering practice. The standards are not up to date with the state of knowledge. There is inconsistency between design standards and practice. There is non-compliance issues, lack of coordination among different non-structural trade persons, and faulty installation, which are not identified in time because we don't have robust quality control measures. So all of these issues actually are contributing towards the sorry state of affairs that we are now regarding non-structural elements. So click again, please. So I would like to finish by saying that actually these problems that we had cannot be solved by improving only a single aspect of the spectrum, and all stakeholders working on non-structural components need to work together. So there is obviously room for a lot of collaboration and work together. Click, yeah, so I forgot to identify, individual industry partners, but we have been working with a lot of industry people in different projects. Like, for example, in sprinklers, we did work with Hilti and Aon and Tracklock, FFP. In partitions, we did work with Lanyon and Lecomte, Winstone. We worked with Hilti as well. Nebulite was our industry partner in glazing, and we worked with Flexitrax from Australia, in addition to Busk pre-stressed concrete and Linen and Lecomte for the cladding panels. There are several others that we did consult and got input, but these are the major partners that we work with. So I think that's where I was going to end and pass on to Rashid, but he did already finish his part. So I will stop there, and if there is any further question related to this part of presentations, I will be happy to take them. Thank you.
Thank you, Rajesh. Yes, any questions? I've got a microphone that should work here. Yes. See if this, pass that back. Should work.
Kia ora everybody. Kia ora, Rajesh. Just a quick question regarding the non-destructive testing, destructive testing and low damage technologies that you're looking at developing. My question is around when you're looking at the framework and then you're also looking at developing these technologies, are you thinking about how modular you need to be in the development of said technologies, especially with the exponential development in our eddy current, ultrasonics, and also the integration of all of those testing technologies within the engineering sector? Big question, I know.
Yeah, it's a big question. Look, I think you have included multiple issues in your question, and
yeah.
I look at the moment. Yeah, I agree. Because at the moment we have got issues in multiple facets of our practice, design and installation practice, and these span across multiple components, right? Not just in partitions or ceilings. It is so. First is actually a general methodology in terms of how we assess or validate the performance of these systems. That is one thing that we need. But when we come back to the system level performance, these obviously the effort now, as you can see from my presentation, is most of the components we try to separate them from each other or from the structure so that they perform independently without huge interaction with the structural performance. So the question comes to, how do we now fill the interface, or how do we manage the interface between one component and the other, or the component and the structure? And that's where the technologies are mainly about connections of the component with the structure, or how do we fill the gap. Still, we have to satisfy the weather tightness, we have to satisfy the insulation, fire performance, so multiple facets of problems. So we need obviously more work, but I think we are on the right direction. We are in the right direction. We are gradually getting there.
That's okay. I will pull that to a close, that session to a close.